I'm sure all of you are aware of the rapid advancement in quantum technologies and especially quantum computing. So you probably heard success stories from the Google lab, the IBM lab, using superconducting circuits, but also other platforms such as cold atoms, neutral atoms, trapped ions. And so you probably also know that the main obstacle today is noise, right? These devices are intrinsically noisy, they're not error corrected yet. And so it is really essential to understand what the sources of noise are and how to mitigate them, right? And so to do so, there is a broad range of techniques essentially to benchmark the correct operation of some quantum hardware. So in like this a simple case where, in the gate-based model where we have a quantum circuit running some algorithm, say maybe prepare some state, then we want to know, for example, how good is the experimental state that we prepare compared to the target one. We might want to know what is the experimental state per se, or we might look at the circuit instead and ask how noisy is the circuit, how far from unitary dynamics it is, or what are the sources of noises, right? And so all these techniques that do that essentially are data-driven. So we go to the lab and we generate data that contains all this information, and then we try to back that out from there. And so essentially they typically face different type of complexities. One is the sample complexity, really how many measurements, how much data do I need to be where I want to be with my algorithm. But remember, those are like classical algorithm running on conventional hardware. So they also face computational complexity in the sense of like really post-processing. And so depending on really the information gain against complexity, you can use various approaches. So on one side, there is really full tomography, where it really gives you the full information about the state or the process, or on the other side, there could be like average fidelities or fidelity witnesses that can tell you how good is the approximation of a certain state, for example, but not really what the information on what the state is, okay? And so today's talk, I'm going to talk about quantum process tomography, so more on the right side of this arrow, and which is the reconstruction of an unknown channel from measurement data. So a quantum channel, maybe a little bit of preliminaries here, it's really the object that dictates the dynamics of an open quantum system described by some density operator. And the quantum channel is its CPTP map. It's a linear map which is completely positive and trace preserving, which essentially enforces that the time evolved density operator is still a physical state. And there are several equivalent representation of quantum channels, and today I'll focus on the Choi matrix, which honestly is something that I was oblivious until a few months ago. What the Choi matrix is, uniquely characterize the channel and is defined as follows. You take a tensor product, say you have n qubits. You take the tensor product of n unnormalized bell pairs, and then you apply the channel to half of them and the identity to the remaining. And so what you get out is rank for n tensor. You have two n indices for the half of the bell pairs you apply the channel, and the other two n indices for where you didn't. So you can divide the indices in this way. And so the properties of the channel directly translates into properties of the Choi matrix. And so particularly if the channel is completely positive if and only if the Choi matrix is positive semi-definite, which means that the Choi matrix is itself a physical density operator just over an extended Hilbert space and not tracing to one because of the definition. And the channel is trace preserving if and only if you trace the output Hilbert space of the Choi matrix, then this should yield the identity on the input Hilbert space. And so in terms of the Choi matrix, you can write down the dynamics of a density operator just essentially by taking the density operator, contracting its transpose with the input indices and tracing. And so what you're left is you just have n indices left, and those are the time evolved, if you will, density operator. Okay. And so particularly geometrics is useful for tomography purposes, maybe more than a Krauss representation, as is going to be clear in a second. So quantum process tomography really translates into reconstructing the geometrics, the full geometrics from measurement data. And so this is kind of the setup we work with. We have a set of input states that we feed to the process. So here you would, I guess you can see my cursor, you would apply some unitary here, for in this case, single qubit. You would prepare this state rho alpha. Alpha is just like an identifier, and you have like single qubit labels there. Then you would apply the process to your input state, and then you would measure some measurement operator m beta at the output. And essentially, if you do this many, many times, gathering this alpha and beta data, and then you would try to back up the geometrics in some classical representation. So we have to store it somewhere. And so the way that this is done is essentially, if you repeat this process many times, really the fundamental object here is this conditional probability, is what is the probability of measuring an operator m beta at the output of the channel, given that the state of the input was rho alpha. Okay, this is just the Born rule here on the output state, but then you can write the output state in terms of the geometrics as this contraction over the input space. And so from here, from the geometrics, you can essentially compute this probability. And full state tomography, what it does is it parameterizes the geometrics in full, really like as a dense 4n times 4n matrix, and then solve this, this fit here where you fit the experimental probabilities just obtained by a histogram with the probabilities obtained from the geometrics, and on with the constraints that you have to have a completely positive and trace preserving channel. And so of course, the full representation scales exponentially with the system size. On top of that, because of this cost function, now the problem is set. Typically, if you want to get good fits, you have to feed a full informationally complete set of input state and measurements. So only a partial information would not work very well in this case. And so what we have done essentially is try to tackle these two problems. The first by introducing a tensor network representation of the geometrics, and the second by using unsupervised machine learning to help the generalization properties of this learning. And so the first step is the tensor network representation of the geometrics. And here we adopted a so-called locally purified tensor network, which was proposed in this paper here, the context of dissipative dynamics. And writing the geometrics this way is essentially boils down to having an MPO, matrix product operator, where each tensor has two bond indices in the bulk. It has a Krauss index, and then the physical indices here, it would be, it's a the difference here, there would be two of them, one for the input index and one for the output index. And the nice property is that if you contract the Krauss index, then what you get is a positive state. So the geometrics written in this way is positive by construction, but it's not trace preserving, that we can enforce that at the level of the single tensor, but I'll come back to that. So the first thing you might ask, well, how far is this getting us, right? So what can we capture with this representation, since we have to work in the limit of small bond dimensions, of course. And so you can easily see that for, let's say the channel is unitary, so it's really just a unitary operation, then you can just go ahead and try to compute the geometrics from here. So say you have some unitary that is compiled in a set of quantum gates, you can contract these gates to build an MPO representation of the unitary, which is going to have some bond dimension that depends on the geometry of the circuit, the depth, etc. Then remember, the way to get the geometrics, you would apply this unitary operation to 1/2 of the qubit in the tensor product of the Bell pairs. And if you do so, because the Bell pairs are just a vectorization of the identity, here we are just applying them to 1/2 of the indices, this contraction is trivial and just returns the MPO itself. And if you then bend the wires around, then you're left essentially with the same structure here, but we don't have any Krauss index. So essentially the geometrics is a rank 1 density matrix, which is what it is for unitary circuits. And so the point here is that if the circuit has low depth and the bond dimension of the unitary MPO is low, then the bond dimension of the geometrics is going to be the same as for the one the one of the MPO without noise. So which means that, we can parameterize sufficiently low depth, say quasi-1D quantum circuits. Okay. So next, the learning part. For the learning, essentially, we use the KL divergence as a cost function while using generative modeling. And so minimize essentially this divergence between the process distribution, this conditional distribution that can be accessed experimentally, and the model, the probability distribution given by our model, right? Which is just an average negative log likelihood. And so for output measurement, we can pick a set of single qubit POVM, those factorizes over the n qubit state. And so this extra index beta would essentially select one POVM. For example, we could choose the 6 eigenstate in the six projectors into the Pauli eigenstates, then this beta index will run over 6 values, which is what we use in the experiments. In the input state, there could be a different set. We choose them to be the same. Just have to be properly normalized by the trace. And so given the Choi matrix here, so the first thing to get this probability, we need to evolve the input state rho alpha using the Choi matrix. We know how to do that. We contract the input indices of the Choi matrix with the input state transpose. And so what this is just the evolved epsilon of rho alpha. And to get the probability, then we use the Bond rule and we contract the output indices with the POVM. For a given alpha and a given beta, this would give us the probability. And these are all local contractions and are efficient as long as the Bond dimensions remain low.
Giacomo, 5 minutes.
Yeah. Oh yeah, thanks. Right. So then, in practice, then what we do is that we generate a data set of this pair alpha and beta, which again, alpha would be an input state where the vector alpha, well, for this case, would be just single qubit eigenstates of one of the Paulis. And beta would be the result, the corresponding measurement and the output. And this is something you can do in the lab easily. Then we can evaluate the gradients of this cost function. This can be done. We did use automatic differentiation in our numerics, but then we're now using the exact gradient because they can be computed efficiently. And then you would just essentially run some variation of gradient descent to minimize this distance and essentially feed the data with this locally purified tensor network. There is just one thing left, is that, yeah, I told you before that this construction does not guarantee necessarily that the corresponding channel is trace preserving, which means that if you trace out the output indices in your tensor network, then you need to get the identity back, which it doesn't by default. So it kind of learns that property from data, but we can facilitate this. And what we can do is that we can take this traced Choi matrix and we can do an MPO subtraction with the identity. And what we are left, this MPO delta, we can compute the Frobenius norm and then take the gradient of that. Essentially, we add with the cost function now would be the KL divergence plus this regularization term. So you're trying to minimize this, meaning you want to maximize the probability of the data. At the same time, you also want to find a tensor network which ensure trace preserving. And as you need to kind of certify this algorithm, we just measure the quantum process fidelity, which is the quantum state fidelity between the parameterized Choi matrix and the target Choi matrix, which we assume we know. So in general, it would be something like this. This would not scale. But when looking at noisy circuit, we use this as we are really benchmarking the algorithm. But typically, if you would compute this other fidelity, which will compare your Choi matrix with the target Choi matrix that you expect to have, and this would scale since one of these two is the ideal Choi matrix would represent a unitary channel, so it would be rank 1. Okay, so we did some experiments, and I'm going to show you some of the results. So here we took a random quantum circuit series from 10 qubits and in 1D. And so each layer essentially consists of, all like random single qubit rotation on every qubit, and then a layer of control NOT gates between neighboring qubits. And then, even an odd layer would like switch the geometry of the control NOT. And so while we train, we can measure here I'm plotting the infidelity for an increasing number of essentially data set sizes and reaching, here would be like 0.99 fidelity, so which is already fairly good for this amount of measurement, which are not very much. And here on the right, we can see essentially the scaling of the infidelity, the best infidelity during the training selected with cross-validation on LDAO data. So it's not the minimum one. As a function of the data set size, as this goes down as we keep increasing the number of samples, of course. And here essentially is the same experiment, but it's a 2D circuit in this geometry where this kind of the structure of the circuit is similar, single qubit, and then CNOTs, and here the CNOTs are applied according to the color scheme. And as we look at this scaling plot with the number of samples, like there is a big decrease in accuracy for depth equal 5. And I mean, this corresponds to a 4-fold increase of the bond dimension of the circuit MPO. So we can see that as the bond dimension grows larger, training becomes harder. And the other set of results are for a noisy circuit where we apply amplitude damping channel to the stabilizer measurement of the surface code, where you have this circuit to measure the X parity check. And at every gate, we apply this local amplitude damping channel. And so here the circuit is noisy. We can see, in fact, that the purity of the Choi matrix decreases as with the rate, the decay rate. And here again is the infidelity. And for no noise, we can get to 0.999, but as the noise increases, then the fidelity degrades at the highest level. But yeah. So I think I'm running out of time. So in summary, we introduce a new way to do process tomography, combining the tensor network representation of the Choi matrix with unsupervised learning. And this scales favorably in the number of qubits. Of course, we are limited by the depth of the circuit in terms of the bond dimension. But for this application of process tomography, this typically is not very limiting, because you don't typically want to reconstruct like massively deep circuits. Spam errors, we didn't really investigate that, state preparation and measurements. And also another open question is really the interplay between the bond dimension and the Krauss dimension in the noisy case. And I'll just conclude by a little advertising. We've been working on an open source Julia code, PastaQ, and I mean, it's not available yet, but it will be soon, and it will feature essentially all of these: process tomography, state tomography with tensor networks, as well as a tensor network simulator for quantum circuits. Thanks.